Okay, so today we're going to start chapter 6, and we're going to start by looking at different types of bonds. So our goal for today is that we will be able to identify the type of bond that would form between two elements and be able to predict the properties of compounds based on their type of bond. So yesterday in our lab, we got a brief introduction to these types of bonds and their properties. So when we did that lab, we should have saw kind of two categories of compounds or two categories of bonding emerge. The first one, these guys were compounds that were able to conduct electricity. Okay, so we saw that light bulb turn on when they were dissolved in water. Okay, and the compounds that had that high conductivity in water, they also shared the property of melting at high temperatures. We needed to put in a lot of energy to melt these compounds. And we should have seen that the compounds that were conductive, they had a high melting point. These guys consisted of an element from the left-hand side of the table and an element from the right-hand side of the table. Or in other words, these were formed between a metal plus a nonmetal. So our examples in the lab were CuCl, Ki, all that good stuff. Okay, that was one main category. Another category we saw these elements that were not conductive in water. Okay, so these guys had a low conductivity or not able to carry that electrical current. The compounds that had a low conductivity also shared the property of melting at low temperatures. So these guys were very easy to melt. Okay. And we should have seen that the compounds that shared these properties that did not conduct electricity, that they melted at low temperatures, these were made from a nonmetal and a nonmetal bonded together. At the end of the lab, we were able to put names to these two groups. Okay, so that first group that was very conductive and had high melting points, these guys were called ionic compounds. Okay. And to those ionic compounds, we're going to kind of add a property that we did not see in full force. The ionic compounds are typically soluble in water. Okay. And then a group with a low conductivity and with a low melting point, and we're made from a nonmetal, these guys were covalently bonded. Okay. All right, and the property we're going to add to these guys is that generally they are not soluble in water. This is kind of a little exception that we see in some compounds. This is where we get the idea that bonding is a continuum. Okay, our label only goes so far. Okay, so not all covalently bonded compounds are insoluble in water. Some, like sugar, are able to dissolve. So we're going to put a little asterisk. So that's the property in general, but we do have some exceptions to that rule. Okay. So now we're going to kind of look and see what causes these two different types of compounds to form. Now that we know our properties of ionic compounds with the ionic bonds, why do they form between a metal and a nonmetal? And now that we know our property of covalently bonded compounds, why do they form between a nonmetal and a nonmetal? How can we predict which type of compound is going to form? Which type of bond will form all lies in something we looked at in chapter 5, one of our periodic trends. So electronegativity is going to be our big driver in chapter 6. So electronegativity from chapter 5 is coming back in full force. So remember, electronegativity is an atom's ability to gain electrons. So if we have a high electronegativity, that means we have a high ability to gain those electrons. we have a low electronegativity, we have a low ability to gain electrons. We don't want to gain them in that case. Okay, so the type of bond that we form all depends on if one of our elements wants our electrons more, or do they both want it equally? Okay, so that's kind of our big question. Okay. Does one of our elements want that electron more than the other? Or do both elements want that electron equally? Okay, so in this tug of war, is it going to be a tie, or are we going to have a clear winner? So if we come over to the periodic table, okay, we are going to see, if we think back to last unit, we can see our electronegativity values for our elements right here at the bottom. Okay? And we can see our metals, these have relatively low electronegativity values. Okay? Our metals do not want to gain electrons. The metals have that low electronegativity. So here they do not want to gain electrons. Okay? However, as we make our way over to our nonmetals, we can see now our electronegativity values are much greater. Okay? So our nonmetals have a high electronegativity. So that means they have a very good ability to gain electrons. Okay. So what type of bond we form between our elements is all going to depend on that difference in electronegativity. How much more does one element want that electron over than the other? Types of bonds. We said an ionic bond is formed between a metal and a nonmetal. Okay? And we just saw metals have low electronegativity, which means they don't want that electron. Whereas our nonmetals have high electronegativity. We're just going to abbreviate electronegativity EN. Okay, so that means we do want to gain electrons. Okay, so since we have kind of this imbalance of desire here, our metal does not want that electron, but our nonmetal really does. Our metal is actually going to transfer its electron to that nonmetal. Or here, let's phrase this better. Our nonmetal is going to take electron from that metal. Okay, remember our metals want to lose electrons. And that nonmetal will happily take it off its hand. So that nonmetal takes that electron from that metal. So now we have a positively charged metal and a negatively charged nonmetal. Because remember, when we lose electrons, that's when we form that positive charge. Gain electrons, we get that negative charge. So since I have a positive and negative charge, I have opposite charges here, our metal and our nonmetal are going to attract to form that ionic bond. Okay. So with ionic compounds, our metals have a low electronegativity. They want to get rid of an electron. Our nonmetals have a high electronegativity. They do want to gain that electron. So that nonmetal is going to take our electron from the metal. Now we have a positive and a negative ion, and they're going to attract to form an ionic bond. See, it's in the name. This is different than our covalently bonded compounds, because we saw a covalently bonded compound had two nonmetals together. Okay? So if we have two nonmetals, both of these are going to have a high electronegativity. So that means they both want that electron. Okay? So since they both want that electron, they're going to end up compromising and they're going to share it. Okay? So where our ionic bonds, we have a transfer of electrons to make everyone happy. Our covalently bonded compounds here, they both have a high electronegativity, but they both want to gain an electron, so they're going to share. Okay? And remember, our whole goal in forming a bond is to make our elements happy to where they have 8 valence electrons. And this is what we're gonna call the octet rule. Everyone's gonna bond so that they have 8 valence electrons. Whether that's a transfer of electrons like in our ionic compounds or a sharing of electrons like in our covalently bonded compounds, nonmetals. Okay? But what do we do with elements that can form both positive or negative charges? Remember, columns or carbon's column, group 4, these guys can all form positive and negative charges. So how will we know what they will want to do, what type of bond they'll want to form in a compound? Okay. So let's say we look at germanium and tellurium. Okay. If we want to find what kind of bond they're going to form, we want to see their difference in electronegativity. So germanium has an electronegativity of 1.8. Tellurium has an electronegativity of 2.1. We want to see how much more electronegative tellurium is than germanium. So we're going to subtract or find the difference between those two electronegativities and find that tellurium is 0.3 more electronegative than germanium. So we can use this chart up here to determine whether we'll form a covalent bond or an ionic bond. So it tells us if our electronegativity difference between atoms is between 0 and 0.4, we are going to form a covalent bond. Okay? So if one atom is only 0.4 more electronegative than the other, they both want that electron equally, they're going to share. Okay? So because that electronegativity is less than 0.4, that difference, this is going to be a covalently bonded compound, and they're going to share those electrons. Okay? However, if we looked at, let's say, beryllium and fluorine. Beryllium has an electronegativity of 1.5. Fluorine has an electronegativity of 4. When we look at that difference, we can see that fluorine is 2.5 more electronegative than beryllium. So fluorine really wants that electron more. So it's going to totally steal away that electron from beryllium and form an ionic compound, because that electronegativity difference is greater than 1.7. So we can another way to double check what type of bond is going to form is we can look at our electronegativity values of the two elements and see, does one element really want that electron more than the other, form an ionic bond, or do they want it equally and form a covalent bond? Different words when we were looking at this chart. Might have seen the word nonpolar covalent and polar covalent. Okay, so these are two different types of covalent bonds, and the difference all has to do with how much our atoms want those electrons. So if we look at nonpolar covalent, we are going to see that there is a much smaller difference between their electronegativity. Okay? So if there's a smaller difference, that means they want those electrons relatively the same. Okay, they have about the same pull. So nonpolar covalent, they're sharing the electrons and they have an equal pull on those electrons. Okay, they both want to gain them equally. So in that case, we're going to share those electrons pretty much right in the middle. If we look at our polar covalent, however, here we have a little bit of a greater difference in our electronegativity. So that means in that covalent bond, one atom or one element is going to have a greater pull or a greater desire on those electrons, okay? And in that case, those electrons are going to lay closer to whoever wants them more. So like for instance, if we were to look at bromine, let's get rid of some of these guys. We were to look at bromine and fluorine. Okay, their electronegativity values are 4 and 2.8. So we have a difference of 1.2 there in how much they want those electrons. Since fluorine wants those electrons more, it has a higher electronegativity. Fluorine is going to pull those electrons closer to itself and form a polar covalent bond. So when we talk about polar covalent, we're still sharing, but we're not sharing them equally. Someone wants those electrons more. So they're both formed between nonmetals, so we're still sharing those electrons. However, in our polar covalent bond, we do not have as similar electronegativity values. So that means one atom or one element wants that electron more. So if we look at chlorine here, he has a greater electronegativity, so he's going to pull those electrons closer to himself, and he's going to hog those. So they're not going to share equally. That more electronegative atoms are going to hog those electrons and pull it closer to themselves. Okay, so if we were to look to see what this looks like, here we can see our electron cloud, so how our electrons are distributed between bromine and fluorine. We're going to see our cloud is a lot more dense near fluorine. That's because fluorine is more electronegative, so it's going to pull those electrons in closer to itself, and those electrons are going to spend more time closer to fluorine. However, in our nonpolar covalent, here we have similar electronegativity values. So these guys are nice. They both want the electrons equally, so they're going to share equally. Okay, those electrons are going to spend equal amount of time around both atoms. So if we have two fluorine atoms, they're the same element, they want that electron equally, our electrons are going to divide its time equally amongst those two, okay? So there's not one element or one atom they're going to spend more time by, they're going to spread out evenly, okay? So again, ionic, metal, nonmetal, great difference in electronegativity to where one atom is totally stealing that electron. Then we have our polar covalent, where they have similar electronegativity values, but one atom still wants that electron more, so it's going to pull it in closer to itself and hog it. And then we have that nonpolar covalent, okay, where here our electrons are being shared evenly in between our elements or our atoms.